This is lecture 1 in BBSP 710. As you can see, the title is Statistical Reasoning in the Basic Biological Sciences. We'll basically be discussing what can go wrong in experiments in science generally and how to interpret the results of studies that may be based on imperfect evidence. And this is probably the most important lecture in the entire course. At the end of the day, if you don't remember how to do a t-test in 6 months from now, that's not the end of the world. You can look it up, you can ask someone else for help. If you get no other skill from this course, I want you to learn how to read a paper critically and be able to see the statistical flaws in the papers. And I also want you to be able to design your own experiments in such a way that you can draw valid conclusions based on these experiments. So I always start with this particular slide that is one of my favorite papers by John Ioannidis. As you can see the title, Why Most Published Research Findings Are False. This paper was published in PLOS Medicine, I believe. The whole thing is worth reading someday if you have some time, but his basic premise, as you can see, is that among other reasons, many scientific studies are tainted by sloppy analysis, that people use inadequate experimental design, try to draw conclusions that are not justified by the data. As a result, we get a very large number of spurious findings in the scientific literature. So today I want to help you understand why this occurs and what you need to do to prevent this from occurring. So, why are most research findings false according to John Ioannidis? Well, there are many reasons, but today I'm going to discuss some of the most important ones so that you're aware of these issues and know to try to avoid them when designing your own experiment and recognize it when you see these problems in other experiments. So, there's a list here. We'll be going through these one by one through the rest of today's discussion. The first issue that can cause problems with experiment is bias. Biased sample is a sample that's not representative of the population of interest. If your sample is not representative, you can get inaccurate results. I'll give a few examples of this as we continue through today's discussion. One example is salary surveys. If you go to the web pages of law schools, oftentimes they'll say that the starting salary of its graduates is over $100,000 per year. I actually had an example of this when I first prepared this discussion a couple of years ago. This indicate that we should all drop out of grad school and become lawyers, or should we be suspicious about this data? Well, if you read the fine print on the website, they acknowledge that there are only 30% of their students who actually return the salary survey. And there's a couple issues with that. First of all, if the students who are working on some big New York law firm making gazillions of dollars are much more likely to let their school know about that than the people who are unemployed or chasing ambulances for pennies or something like that. And the school knows they want to get the best number possible, so if they know that a guy is working on a corporate law firm in New York City, they're going to send the salary survey to them 5 times to make sure they actually fill it out. Somebody who's unemployed, maybe not so much. So the net result is you end up with wildly optimistic salary estimates. Something closer to what one may encounter in the context of biomedical research. Let's say you want to look at biomarkers, some sort of genetic assay, tissue assay, whatever, comparing people who have disease to controls who don't have the disease. So you go through to your local clinic and you recruit people who have the disease, but to recruit controls, you just recruit from the general population. You set up flyers on campus, tell them to come in and get their blood drawn, whatever the case may be. Do we get a representative sample if we do this? Well, it's been well documented over the years that people who come into a clinic are not representative of the general population. Among other things, women are more likely to go to the doctor than men. Educated people, wealthy people are more likely to go to doctors. Obviously, if you don't have health insurance, you're far less likely to go to the doctor. So it makes it very difficult to tell if a biomarker is actually associated with the disease or if it's just associated with gender, race, or class, or something along those lines. Another good example of this is asset prices. If people bought tech stocks in the late 90s or houses in the mid 2000s, thinking they would become rich really fast, well, if you pay any attention at all to the news, you know that that turned out very badly for them. That indicates that you should not assume that a trend in your data will be generalizable to different times or different places. This is known as extrapolation and can give you incorrect results, which we'll discuss in more detail in the future. What to remember about bias is that any statistic and the best statistical analysis in the world is meaningless if the sample is not representative of the population, or if there's some sort of systematic measurement bias. So you want to make sure that your sample is as representative as possible. Now, in practice, this may not always be possible if you want to, for example, sample from, if you want to do a presidential election poll, you would need to sample from the universe of all possible voters in the US. Some of them don't have phones or any way to contact. That would be completely impossible. So virtually any sample you ever encounter will have some level of bias. The important thing is to try to do everything in your power to reduce this bias so that your results can still be generalized. And that's a difficult area to figure out, and you'll probably have to learn that with practice. But in general, whenever you look at a study, you should ask the question, is this sample representative? If it's not representative, how will that affect the conclusions of the study? Another issue that can cause problems in scientific experiments is outliers. An outlier is an observation that's extreme compared to the other observations in the data set. If you look at the slide here, you can see two outliers at the far right of the graph that have values that are much larger than the other data points. And some of the most commonly reported statistics, particularly means and standard deviations, are not resistant to outliers. If somebody just reports a mean and doesn't take outliers into account, the mean can be highly misleading. So let's go back to the salary survey example. That say a law school reports the average starting salary of its graduates was over $100,000 per year. Well, let's say that 1/3 of their graduates earn $200,000 per year and the other 2/3 earn $50,000 per year. You would still have an average of $100,000 per year. But that would but if you went to law school thinking that you're likely to earn $100,000 per year, you could be in trouble because 2/3 of people would not actually do that. And is this just an issue of law schools wouldn't actually be that evil, right? I mean, if you would assume a survey that large, it would all balance out. Well, they actually, a legal organization actually did a study, and here you see a graph of the distribution of starting salaries for lawyers in the class of 2007. You see there's a very small peak of people who ended up at a major law firm earning about $160,000 per year, but the overwhelming majority of people earn far less than that. The median was only 65,000. The average was probably even lower, indicating the overwhelming majority of new lawyers earning closer to $40,000 to $50,000, not $160,000. But if you just take the raw average, you end up with an average that's much higher. So the thing to remember about this is that even a small number of outliers can have a huge effect on means or other statistics, you want to check for outliers before you do statistical analysis, and if you find outliers, you need to deal with them appropriately. And this sounds simple in principle. In practice, it's very hard. The question of whether or not you should remove an outlier depends on the problem that you're working on and a number of other things. I will discuss this in more detail later in the course. Another thing that can cause problems when performing statistical analysis is measurement error. That anytime you measure anything, there's going to be a certain amount of measurement error. Hopefully the measurement error is low and it won't affect your conclusions noticeably, but you have to keep your measurement error in mind when you consider results. An example that seems kind of silly, but actually happened once, is that once upon a time, Reader's Digest performed a study on the amount of nicotine and tar in various brands of cigarettes. And they basically found no differences whatsoever, but Old Gold won by a hair, having a slightly lower amount of nicotine than other brands. So they used this as an advertising campaign, even though the difference between the amount of nicotine in Old Gold and the amount of nicotine in other brands was within the margin of error of the study. An example that's more relevant to biological science is a genome-wide association study. I actually read a paper on this. It was a genome-wide association study looking for risk factors for prostate cancer. So they looked at like 1,000,000 single nucleotide polymorphisms to see which ones were associated with prostate cancer. They identified the 10 quote-unquote most significant SNPs. And the relative risk associated with carrying these SNPs was enormous, something like 1.6, 1.7, but can we actually believe these numbers? Well, the problem is when you look at millions of different SNPs, some of the SNPs are going to produce very large odds ratios just by chance. And in a certain sense, to be at the top of a list of 1,000,000 possible SNPs associated with prostate cancer, you have to be both lucky and good, in the sense that you have to be good, quote unquote, there probably has to be some true association. You also just have to get lucky that the effect was unusually large in this particular sample. And if you look at the margin of error associated with the estimate, the true value is likely to be on the low side. When they tried to replicate these studies, some of the SNPs couldn't be reproduced at all, and the ones that were reproduced had much smaller effect sizes than what was observed in the larger studies. Well, the things to remember are that when you're reporting a statistic, you have to keep in mind the associated standard errors. And this is particularly important when you compare the results of multiple experiments or derived statistics like odds ratios. Another thing that can cause problems is if you simply measure the wrong thing. Oftentimes, when you're doing science, you can't measure a variable directly due to ethical problems or cost problems or the fact that it's just physically impossible. You have to try to measure it indirectly. And you like to believe that this other variable will provide the same information, but sometimes this won't be the case. A classical example of this is surveys about drug use. You can't directly observe the proportion of people who use drugs, so instead you just have to do a survey and ask people if they use drugs. And these results will obviously be invalid if people lie, and there's some research indicating that people do lie on surveys about sensitive topics like drug use. A simple way to get around this is when you administer your survey, you can say something like, flip a coin, and if it lands heads and you've never used illegal drugs, then say no, otherwise say yes. That way the person interpreting the data won't know if you say yes, if you really use drugs, or if it's just because the coin landed tails. And there have been some studies showing when you use that type of design, the proportion of people who use drugs is much higher. Another issue where you can get into trouble, which is very common in the biomedical world, is animal models. Oftentimes people will conduct experiments on rats or other animals to try to learn about humans. And there's no good alternative in many situations, but sometimes a drug that works well on rats won't work in humans or it'll cause dangerous side effects in humans. So, measuring a variable indirectly is oftentimes a necessary evil in science, but you want to try to verify as best you can that the variable that you observe is a good surrogate for the variable that you didn't observe, and use caution. You have to use caution when interpreting the results. And when you read a paper, you always want to ask this question: are they directly measuring what they want to be measuring? If not, what should they have been measuring instead? And is what they actually measured a reliable indicator of what they're actually trying to measure? Another important part of experimental design that hopefully most of you know already is when you perform any type of science experiment, it should have controls. You control represents something like a baseline. Either they don't get a treatment or they're people without disease, whatever the case may be. If you don't include controls in an experiment or you do a bad job of choosing controls, that can give you inaccurate results. An example of this in the medical literature were some early experiments on a procedure called the Portacaval Shunt. And the Portacaval Shunt is used in cases of cirrhosis of the liver, which can cause people to hemorrhage and bleed to death. And to try to keep them alive, you can redirect blood through this shunt. But in order to do that, you have to do a long, hazardous operation where lots of things can go wrong. Some people wondered, is this really even worth it? Or do the risks of performing the procedure greater than the risks of using other methods to treat the hemorrhaging? So, at one point, there was a meta-analysis that collected about 36 studies that have been performed on the Portacaval Shunt and looked at whether or not they liked the procedure and also whether or not there were controls in the study. The vast majority of the papers did not include controls. It was just something like, yeah, we applied a Portacaval Shunt to these 10 or 15 people and they all survived and it was wonderful, awesome. And among the papers with no controls, the vast majority liked the procedure. 24 out of 32 said it was a fantastic procedure, and one was moderate, and almost all the remaining were moderately enthusiastic about it. There was only one study without controls that recommended against the procedure. However, among the studies that included controls, there was only one that recommended it at all, and the other three said, no, it's not worth the risk, suggesting that when you compare people who got the shunt to people who did not get the shunt actually did not work nearly as well as one might think. Another, and even if you have controls in your study, you can still have problems if your controls are inadequate. This is a true story of a study that I worked on several years ago. We were trying to identify genes or genetic markers that were associated with increased risk of developing fibromyalgia. And I got the data and was completely oblivious to the study design and ran a model, looked for SNPs associated with fibromyalgia, and found a set that were just absolutely off the chart in it's, it's an incredibly strong association. The point that people had all these markers had almost a 50% chance of developing fibromyalgia. I got super excited and was having visions of appearing in the New England Journal and so forth. And then I talked to my collaborator and he said, Eric, that particular marker is an ancestry informative marker, and that other one was just a quality control marker. Those should not be associated with fibromyalgia. Double check your results. Well, after some discussion, we finally figured out that what was going on is that the fibromyalgia patients were recruited and genotyped at one location, and the control samples were recruited from different studies and genotyped at a different location. And the incredibly strong association that I had found with fibromyalgia, I had actually just found an incredibly strong genotyping patch effect, which was a bummer. So the take-home message is that any experiment should have controls in some form or another, and you want the controls to be as similar as possible to the treatment population, with the obvious exception of the treatment itself. We'll discuss this in more detail in the next couple lectures, that the gold standard is when there's really no difference at all between the treatment and control groups, but frequently that's not possible, particularly when you're doing studies involving humans. Stay tuned to the next couple lectures and we'll find out about this in more detail. Another thing that can cause problems is multiple hypothesis testing. If you have any familiarity with statistics, you'll know that in statistics, often we perform statistical tests and we calculate a p-value. And the p-value is basically the probability of observing as big of a difference as we observe between our treatment and control groups, assuming that there's really no difference between the two. If you've never heard of this before, don't worry, we'll discuss this in much more detail later on. But by convention, if your p-value is less than 0.05, then you say that your findings are statistically significant and that there really is a difference between the treatment and the control group. The problem with that is it means that we're wrong about 5% of the time. And if you're only looking at one particular thing, that may not be a big deal, but it's a much bigger problem when you're testing multiple hypotheses. A famous example of this in the psychological literature is an early study on schizophrenia. Researchers gave a psychological questionnaire with 100 questions to patients with schizophrenia and some controls who didn't have schizophrenia. For 4 of the questions on the survey, there were differences between the two groups, the p less than 0.05 level. The researchers immediately ran out and published these results. What's the problem here? Well, if you think about it for a minute, if you do 100 different hypothesis tests and you're wrong 5% of the time, then you would expect about 5% of 100, or about 5 of the significant findings, to be false positive. In this case, 4 of the things were significant, which is about what you would expect due to chance. Oh, these findings turned out to be spurious and were never reproduced. Well, the moral of the story here is that when you're testing multiple hypotheses, the conventional p less than 0.05 criteria may not be good enough to avoid false positives. This is particularly relevant in the bench science world when you're using huge numbers of tests, when doing things like microarrays or genome-wide association studies, things like that. Even if you perform a single test, you should always ask yourself if a p-value of 0.047 is really significant, or if it could just be a fluke. Another major problem, and perhaps the single biggest source of spurious scientific findings, is an issue known as confounding. Confounding is, in science, oftentimes you want to say, is variable A causing variable B, or somehow associated with variables B. In confounding is when there's a variable C, the variable at the bottom of the graph in this figure, that affects both variable A and variable B, and you can't be certain which is the cause and which is the effect, or if there's no association at all between A and B, and they're simply caused by variable C. This was this is a picture that made me laugh, of something that a friend of mine posted on Facebook a while ago. Some of these examples are a little bit dated now, but it illustrates why it's dangerous to assume that just because two things are strongly correlated, that one causes the other. Look in the top left corner, you can see that the interest rate on Greek debt is follows closely with the number of Facebook users. Or if you look at the budget for the National Science Foundation, it seems to be increasing at approximately the same rate as temperature, lending credence, one might think, to those people who say that global warming is some sort of conspiracy caused by scientists, something I've never really understood. Or if you look at like the number of people who read newspapers and the average rating of M. Night Shyamalan's movies on Rotten Tomatoes, as you can see that back in 1999, The Sixth Sense was a fantastic movie and people were buying tons of newspapers, versus 2010, suddenly newspapers are earning far less money and M. Night Shyamalan is making The Last Airbender. Lower right corner, you can see how a mountain range correlates with the murder rate in New York State. Some other examples that you might run into in the scientific context, there was a study once that found that children with larger shoe sizes scored better on certain achievement tests, and the researchers scratched their heads for a while and couldn't figure out why that would be the case until they realized that shoe size and test scores are both correlated with age. In this case, age was the confounding variable, and there was no true association between shoe size and test scores. Or another example, I read an op-ed once about funding for public schools in California, and this columnist noted that schools in California that got the most money per student consistently had the worst test score. He tried to argue this proves that teachers aren't underpaid, that just throwing money at the problem will not improve the quality of education, and blah blah blah. But is that really justified based on this data? Well, as it turns out, schools that get the most money from the state tend to be the schools with the largest number of special education kids, or the schools with large number of kids for whom English isn't a second language. They get extra money, and obviously special ed kids and kids that are learning English tend to not do as well on standardized tests. This isn't good evidence that increasing funding for schools won't improve results. It just shows that right now extra money is being targeted to the neediest schools. An example that's closer to science, and another blunder that I made earlier in my scientific career, was we did a genome-wide association study looking for genes that are associated with the increased risk of developing arthritis or more severe arthritis. So I got the data set, compared the people with arthritis to people with less severe arthritis, and found a huge number of SNPs strongly associated with the condition. In this case, the numbers were so drastic I didn't even have any delusions of New England Journal papers. I knew something had to be wrong. The mistake here was that African Americans are more likely to develop arthritis, and they also have some genetic differences from Caucasians. So the vast majority of the SNPs that I found were actually indicating your racial ancestry, not indicating whether or not you're likely to develop arthritis. So what you need to remember here is that correlation does not imply causation. Just because two things happen at the same time does not mean that A causes B. And there's no statistical tests for confounding. You just have to use common sense here. Anytime you read a paper, you should ask yourself, is it possible that there's some confounding variable that the author has overlooked that could cause the association that we observe here? Another even more fundamental issue is what I call torturing the data. This comes from a famous quote by Nobel Prize winning economist Ronald Coase, who said, if you torture the data long enough, if it will confess. And basically some researchers tailor their statistical analysis to try to prove their hypothesis rather than looking at the data itself and trying to determine what the data actually says, even if the data says something that we don't like. I always like to use this particular comic to illustrate why this is dangerous. That if you assume that you're flying into a cloud when you're actually about to fly into the side of a mountain, that could produce catastrophic results. Why does this happen? Well, if you've spent any time in academia, you know that there's enormous pressure to publish, or if you're working in industry, there's oftentimes pressure to show that a particular drug or device or whatever you're looking at is effective. And if you invested 6 months and a lot of money on an experiment, there can be a really strong temptation to try to do something that makes it look like your experiment was successful rather than just say that your time and money was wasted and the experiment was a bust. And people who succumb to this temptation will succeed in the short run and sometimes even in the long run, but it's a bad idea on both ethical and practical grounds, aside from the fact that the ethics of publishing false information to advance one's career are bad. It can come back to bite you later on. Some famous examples of this in the history of science is probably most of you are probably too young to remember Fleischmann and Pons and cold fusion, but the basic story is that they saw something in their data that they thought was cold fusion and ran and told the media about it, but quickly they realized the results could not be reproduced and they ended up with major egg on their faces. A more recent example, if you've read about the case of Mark Hauser at Harvard, was one of the most famous primatologists in the world, but he's since been censured for scientific misconduct and his career may be over because basically he was looking at videos of his primates and said he saw things where the primates behaved in a certain way that anyone else who looked at the tape just said, oh, that's just spurious, there's nothing going on there. And this world famous scientist's career may be over as a result of this. So don't let your name be added to this list. Always try to make sure that your findings are backed by rigorous statistics, and even if the data indicates that your experiment failed and that the hypothesis that you were trying to prove turns out to be incorrect, it's far better to just acknowledge that than to try to torture the data to produce some spurious findings. Next couple lectures will discuss experimental design in more detail and what things that you need to do in order to design a proper experiment to reduce the risk of having bias or confounding in your final results.